So far we have covered decoders, and as we know that decoders, they are a logic circuit that detects the presence of a specific combination of bits at its inputs. And in the class we have covered, basic decoders that we have 2 to 4 decoder, 3 to 8 decoder, and we covered the discussed the timing diagrams, how the output varies with respect to the input. So now our next topic is, and yeah, we studied also the cascaded 3 to 8 bit decoder in order to generate a 4 to 16 decoder. So now the next topic, or shall we say the last topic of in decoders is, BCD to 7 segment display. So this particular IC is very useful whenever we need to interface a 7 segment display in our system. So we use this particular IC in the middle. This is the BCD to 7 segment display IC, and then obviously 7 segment will be connected on its outputs. So these are the inputs, BCD inputs, BCD, binary coded decimal that you have. So these are the inputs for BCD, and these are the outputs that will be connected with the 7 segment display. A to G, as you can see here, these different, output pins will light up that particular segment. A to G outputs are designed for much higher current than most devices, hence the word driver. So basically, this IC is also a driver IC as well to provide a higher current. Um, okay, so this is the connection of the 7 segment display with this IC. Um, Notice that the current limiting resistor is required to prevent overriding the LED display. So we have these current limiting resistors here connected between the 7 segment and the IC as well. Now, our core discussion now is going to be actually with regards to these particular control lines, LT, BI, RBO, and RBI. And what do they mean, what different functions we can achieve with these. So we'll discuss that. But before I go on to this, I'm pretty sure that you all understand how these inputs will be reflected here, right? So if it's all zeros, then accordingly a zero will be generated, zero pattern will be generated, and for that A, F, E, D, C, and B, these segments will light up. So this is the job of the IC to translate it into the relevant pattern, okay, relevant output on these lines. Now once that's covered, now let's talk about the control lines. Now in the control lines, the first important line is this lamp test input. This is lamp test input, this is blanking input, this is ripple blanking output, and this is ripple blanking input. Okay, now LT, BI, and RBI are inputs, only RBO is output. Okay, so they are all low enabled. Okay, and yeah, so they have different features. Now let's talk about them. Oh, before we do that, this is just I put this particular table in here just to indicate that if you zero, this is how your segment and output lines will be generating the output. Okay, so for 0, all of these segments will light up. For 1, only B and C will light up this particular segment. For 2, uh, basically A, B, G, E, and D will light up. So you can, figure out from this as well yourself. You don't have to memorize this, obviously. For F, for example, which one will be? A, F, E, and G. So you can see here A, E, F, G. Yeah. All right. Now the lamp test. Um, Instead, let's yeah cover this one. So we have the lamp test in order to check basically the whether our segments lights are working fine or not. So basically, this is the purpose of the lamp test. Okay, yeah, I talked about the 3 control lines. Lamp test feature is built in this IC, which checks the segments basically. So whenever the lamp test input is low, because as I said, it's a low enable, all of these control lines are low enable. So when it's low, when low signal is provided on lamp test, then um, basically what happens is that all of these segments light up. Okay, all of these segments light up. When the switch is in zero position, it enables the LT feature and all segments light up. Okay, and it overrides the conditions at DCBA. What is DCBA? This, meaning if you have some input, you're receiving some input at this IC on the input lines, but your lamp test is enabled, meaning it is connected with the ground, then this will be overridden. This will be neglected, you can say. Okay, this will not be displayed here. 5 will not be displayed. Instead, it will light up all the segments. Why do you have this feature? Just to check, as I said, just to check, whether your LEDs are working fine or not. Okay. All right. So this is the feature of the lamp test. As I repeat, it's low enabled. When it is connected with the ground, then all the segments light up and the input lines are overridden. Okay. However, if it is connected with 5 volts, then whatever is on the input lines, that is reflected on the output lines. Okay. Okay, so after lamp test, so this is the feature of the lamp test. Okay, now the next, important control pin is BI, which is the blanking input. Okay, decoder BI input is the blanking input. In the blanking input, this is also active low pin. Okay, so you can connect it with a switch, just like lamp test, and you can flip it, according to your requirement. Okay, so if it is connected with the ground, then it enables the blanking input features. And what it does is that again it overrides the input, however, it turns off all the segments. Okay, the name I think indicates, blanking input. It blanks out the input. Okay, so it blanks out these inputs. Okay, it doesn't display anything if it is connected with 0. However, if it is connected with 5 volts, then obviously this feature is disabled, and whatever is on the input lines will be displayed on the output lines. Okay. All right. Now the other feature is RBI. Okay. BI, is normally used if, you have multiple segments. However, you don't intend to use certain, segments on your circuit. So you can simply, just blank them out. But there's another feature which is used differently, which is ripple blanking input. It is used in conjunction normally with RBO and RBI. Okay, so RBO is the ripple blanking output. It works with RBI to blank the number 0. Basically, this is the reason, why we use RBI and RBO. So if I just recall, what did we discuss so far? The lamp test. Lamp test is to check the different segments are lighting up fine or not. So that is low enable. You can connect it with the ground to check your segments. It will light up all the segments. That is lamp test. Second was blanking input. If blanking input is connected with the ground, then all your segments are turned off. Okay, that is an input. Then there is another one which is ripple blanking input. Now ripple blanking input and ripple blanking output, these two lines, they work in conjunction. Okay, and they are used to sort of control, the trailing zeros and the leading zeros. Yeah, that is basically zero suppression. Okay, zero suppression is done in using these two lines. Okay, so yeah, basically, so if you have, if I can use the pen and indicate it to you, that if you have a number like this, 0, 0, 1.400. Now, so basically the number is actually 1.4, but in 7 segment, if this is how it will be displayed if you have like three segments to indicate the non-fraction part and three segments to indicate the fractional part. This is how your number will be displayed, but you don't want these zeros to be displayed. Okay, you don't want these zeros to be displayed. Now these are called as leading zeros. Okay, these are your leading zeros and these are your trailing zeros. Okay, so we don't want number to be displayed like that. So this is called as zero suppression, leading zero suppression and trailing zero suppression. So basically this will be achieved using RBI and RB0. However, if you have a number like this, 10.400, yeah, so basically the number is 10.4. Okay, this is the number 10.4. So now this is a useful zero. We can't get rid of this. Okay, so this is an essential zero, so this will remain, right? So if you understand this concept, then we will see how this is actually implemented. Okay, how this is actually implemented. Okay, now keep in mind LT is a separate line. However, although in figure purposes BI and RBO are shown separately, however BI and RBO, they share the same line. So at one time only one of these will work. So basically one line, if I show you the previous diagram, the actual IC diagram, as you can see here, BI and RBI are actually, they share a line. So this line will either act as input or output. So if it is acting as input, we are only using BI feature. If it is acting as output, or if you want to use RBO feature, then it will act as output. Okay, so at one time we are using one of these two features. Okay, so obviously if we want to use RBI feature, then we have to use RBO with it. Okay, all right. Now going back, I will repeat it all, don't worry. It's very simple concept, nothing complex about it. So RBI LT lamp test done. BI blanking input. It just blanks out the input. Okay, and displays nothing on the segments. Now we're talking about RBO and RBI and RBO. Now RBI, it's a ripple blanking input. Now again, you can connect it with a switch. Again, this is a low enable line. So if you connect it with 5 volts, obviously this feature is not being used. You're not using this feature is disabled. It will only be enabled if you connect it with ground. So when it is connected with ground, then this is enabled. What does it mean that it is enabled? So what will happen is it blanks out the input, but only zero input. That's the beauty of it. Okay, BI was blanking out any input. RBI only blanks zero. Okay, I repeat, BI that I discussed beforehand, yeah, before this, BI blanks out any input. As you can see here, when BI is connected with zero, anything on the input lines will be blanked out, meaning it will not be displayed. However, RBI and RB0, they are only for leading, suppressing leading and trailing zeros. So when RBI is connected with ground, okay, when it is connected with ground, as you can see here, let me use the, yeah. So when it is connecting with zero, so when the switch is in zero position, it enables the RBI feature and RBI blanks the display for number zero. So if you have zero here on the input, that zero will be blanked out. It is lighting up here because it is connected with 5 volts. So if RBI is 5 volts, if it's a 0, it will be displayed. However, if RBI is connected with ground, then this 0 will not be displayed. Okay, as you can see here. Sorry, there you go. RBI blanks the display for the number 0 when the switch is in 0 position. All right. Okay, so this feature, why is it useful? Because I told you, it will blank out the leading or trailing zeros as well. I will show you using examples. And yeah, one important thing also here to notice is that whenever RBI is 5 volts, this it is disabled, then RBO is 1. That means that we are not blanking out any output. on the 7 segment. So RBO is 1. However, whenever RBI is enabled, it is connected with ground and you are suppressing a 0, then a 0 will be enabled here. Okay? You have to remember this thing that RBI is a ripple blanking input, and RBI and RBO are used in conjunction to suppress leading and trailing zeros. Okay? So if RBI is connected with 5 volt, which means that it is not active, it is disabled. So when that is the case, then whatever number is here, it will be displayed. And if there is a 0, it will be displayed. Okay, as you can see is written here. Okay, when the switch is in 5 volt position, meaning RBI is high, it is receiving high input, which means RBI is actually, this functionality is disabled. So if there is a 0 or any number, it will be displayed. However, if it is connected with ground, 0, which means that RBI feature of this IC is enabled, what will then this feature, do? If there is a 0 on the input, it will be blanked out. It will not be displayed. Okay, so when the switch is in 0 position, it enables the RBI feature. RBI blanks the display for number 0 only. That's the important thing, only for number 0, not for other numbers. Now, what happens then? RBO pin outputs a logic 0 signal to display that, there is nothing being displayed on our 7 segment display. Okay, let me just try and summarize it in a yeah, here. So when RBI is 0, okay, which means that it is active, it is enabled. Yeah, so what happens? 0 means enabled or active. Then one of the two things happen. First is that A, B, C, D lines, the input lines have 0 on it. If A, B, C, D lines have 0 on it, the output lines, which is A, B, C, D, E, F, G, they become blank. Okay, they are blank. At the same time, RBO line also displays a 0 to indicate that our display is blank. This is condition number 1. The other condition is that ABCD has some other value other than 0. Okay, some other number, 1, 2, 9, and A, B, C, D, E, F, G. What will happen to that? It will be displayed. Whatever the number is, it will be displayed. And what will happen to RBO? It will be 1. Okay, so basically this RBI features only blanks 0. If there is a 0 at the input, the output will be blank and RBO will indicate that our output is blanked. However, if there is some other number on the input lines, but this feature is enabled, but there is some other number on the input line, it will be displayed as it is and RBO will be 1. Now the other situation is that RBO, which is low enabled, is actually 1, which means that it is disabled. This feature is disabled. So in this particular scenario, again the same thing will happen. Whatever, I think I can simply just point to the same thing. I don't have to write it all over again. So basically the same thing will happen. Oh, I'm sorry. Just a minute. Yeah, here. Okay. So the same thing will happen actually. Okay, the same thing will happen. Whatever is on the input, if it is disabled, but the thing is, in that case, 0 will also be included. So if there is a 0 on the input, it will be displayed. I think it's best I write it separately because slightly different situation. So it will be like this. No matter what the value is from 0 to 9, the output will display that value. Okay? And RBO, since output is being displayed, so it will show 1. Okay? So this is basically the whole concept. All right? What other thing we talked about? The other thing we talked about was LT, and I showed you that LT is also low enabled. Whenever it is 0, uh, A, B, C, D, F, G, the outputs will become all high. This this will be okay. All of these segments will be high. Okay, no matter what the input is. Whatever is on the input, it doesn't matter. It will be overridden with these values. Okay. However, if it is, so obviously 0 means that it is active or enabled. Okay. If LT is 1, then obviously it doesn't matter. Whatever is the input will be the output. Similarly, for blanking input, if blanking input is active or enabled, okay, if that is the case, meaning again active, I'm writing both the words. In the previous slide, I used the word enabled. Yeah, enabled or disabled, and this is active or inactive. It's the same thing. So that means if blanking input is, enabled, then that means whatever is the input, it will be blanked out. Nothing will be displayed. Okay. So hopefully this is clear to you, that what is the difference between these different, concepts. All right. Now moving forward, I will just show you quickly the example. What is the example of this concept of blanking input and blanking output. Now the number is, as you can see here, 00307. You have because you designed your hardware in a way that you knew that you could have 5 different values to represent or to display. So you put 5 segment display. Now you do not want a situation in which a number 00307 is displayed like this, 00307. You want it to be displayed like 307, like a normal number. So these should be blanked out. How should it be blanked out? So again, we will use the feature of RBI and RB0. Okay, so these are since leading zeros, meaning they are coming before, this before decimal basically, for the whole number. So these are leading zeros. Now you want to blank them out. So what you will do is you will connect the RBI with the zero. So first RBI will be enabled. Okay, now what is the situation I told you? If RBI is enabled, what happens? If the input is 0, it will be blanked out. If the input is not 0, that input will be displayed. So this is exactly what will happen. Now RBI is enabled here. What is the input? The input was actually 0. So since it was 0, it will be, what is the input? Input is actually displayed here as well, right? This is the value, okay? Control pen. Yeah, so this is 0, this is 0, this is 3, this is 0, and this is 7. Okay, so these are the numbers being displayed. So this is 0, so the input is 0. This is enabled, so it will be blanked out. Since it will be blanked out, RBO will be 0, and this is exactly what I said, right? So if it is blanked out, RBO will be 0, right? If it is not blanked out, RBO will be 1. Okay, so now this is 0. So now this 0 will be fed into the next RBI. Okay, so it automatically enables this feature for the next IC. And it tells this IC that now, since my display was also blanked out, so it is a possibility that your display could also be blanked out because you could also be receiving a leading 0. So now again, if there is a 0 on the input, it will be blanked out, and since there is a 0 on the input, this feature is enabled. Blanked out, output is blanked out. Output is blanked out and RBO is 0. This is what I explained to you here. If RBI is enabled, input is 0, output is blank, RBO is 0. This is the situation happening here. Again, this RBO will be fed into the next RBI. It will be connected with the next RBI. Now, here RBI is enabled, but the input is a number 3. It's not 0. So what happens? It will be displayed, as I told you here. It is enabled, but there is some input value. It will be displayed. It will be displayed and RBO will become 1. RBO, as you can see here, becomes 1. Okay, so the IC says that my RBI is enabled, but I'm not receiving a 0 on the input, so I will display my number as it is. And RBO basically indicates what? That the display is showing something. It is not blank. Okay, so this is 1. Now this will be informed to the next IC that now leading zeros are done. Okay, now we have a number. So numbers are starting. So if a 0 comes, then don't consider, it like a blank, a leading or trailing 0. So now RBI is disabled here. There is a 0 on the input, but RBI is disabled. If RBI is disabled and there is a 0, it will be displayed. You see here, RBI is disabled, input has 0, it will be displayed, and RBO will be 1. This is what's happening here. You receive, your RBI is inactive, you have a 0, will be displayed because this is it's an essential 0. It's not a trailing or a leading 0, so it will be displayed. Now again, accordingly, because it will be 1, because we're not blanking it out, so it will be 1. Now for again next IC, um yeah, so it should be connected with the next IC, and then again you have a number, again you have a number. I think there's a mistake here. It should not be like that. It should be connected with with this one. Okay, so what will happen here? Again, you will say that, this is a number. RBI is disabled. RBI is disabled, so the number will be displayed. Okay, so the number will be displayed. And oh, I think, yeah, what they've tried to do is that, here in any case they have disabled this RBI, because this is, they don't want that, if it's only 1 0, then it should be displayed. Okay, so but basically this is what they've tried to do it, that the last 7 segment display, they have disabled the RBI, that no matter what, if it is 0 or whatever, it should be displayed, because normally RBI we enable so that the leading and trailing zeros should not be displayed. Okay, now RBO is 1 again, and that's about it. This is the situation, this is the example. It's the same example, I mean, the same situation being explained here again, the same thing. As you can see, RBI is here, they haven't done that thing, what they did here. Here it is connected. So as you can see here, first, RBI is enabled, and then accordingly, based on the values, you keep connecting the RBO with RBI, this RBO with this RBI, this RBO with this RBI, and it'll, suppress the leading zeros. Okay. It's the previous example was much more detailed. That's why I put it. Actual example was this in the presentation, but I thought that that one is, explaining it much better way. So depending on the display type, current limiting resistors may be required, for obviously for these outputs. Now this is for trailing zeros. For trailing zeros, you start from this direction, right? What are the trailing zeros? I just had told you that if you have a situation like this, 4 0 0, these are trailing zeros, these are leading zeros. So for trailing zeros, this is the situation. So you start obviously from this side, you're starting from this side. Okay, so you have, so we're assuming that, this is after, see here, this is the decimal here. So these are the numbers after the decimal. Okay, so after the decimal, these if there are zeros here, it will be trailing zeros. As you can see here, the number is what? Number is 5700. These are the inputs, right? These are the inputs. So you will start from this side. Okay, so you will enable the first RBI, just like we did it for the leading zero. Enable the first, and then for the rest, just keep connecting RBO of the first IC with RBI of the second IC, RBO of the second IC with RBI of the third IC, and RBO of the third IC with the RBI of the fourth IC. So it is the same procedure as we did before. It's just starting from this side. So if you have a 0, obviously it will be blanked out. It will be blanked out. Our RBO will become 0 to indicate that we have blanked our output. The 0 will enable this RBI for this IC. Okay, now if this IC has a 0, it will be blanked out. If it doesn't have a 0, it will be displayed. RBI is enabled. Now, since we have blanked out, so RBO will become 0. If we don't blank out, RBO will be 1. So now it is 0, so it will feed the next RBI. Okay, now RBI is again enabled. However, the input is not 0 because RBI only enables, only blanks out zeros. But this is a number 7, so it will not be blanked out. It will be displayed. And similarly, and obviously now here, because we're not blanking anything, so RBO will be 1. And then that will be fed here. Okay, so this is the situation here. Again, because this is 1, so this RBI is disabled. This is disabled, so even if there is a 0 here, it will be displayed. Just keep in mind this particular, a figure that the conditions that I've written. So if you understand this situation, everything will be clear. Okay, now we will move on to encoders. Okay. Now, what are encoders? We're done with decoders now. So far in this chapter, we have covered adders, half adders, full adders, parallel adders, ripple and carry ahead adders. After that, we covered comparators, right? After comparators, we did decoders, and decoders we did in quite in depth. All sorts of decoders, cascaded decoders, and then we did this BCD to 7-segment decoder. So now that's done. The next step is for us is to cover the encoders. Now, encoder is the reverse logic of decoder basically. So an encoder accepts any active logic level on one of its inputs, and convert it into a coded output. Okay, so it receives input, on one of the inputs and then convert it into some kind of a code on the output. Okay, because we are encoding, we are coding it, we are making it more complex. Decoding is we are making it simpler, you can say. Yeah, so it was a we are decoding a circuit. That was a decoding circuit. Now this is an encoding circuit. Okay, this is an encoding circuit. So the decimal to BCD is an encoder with an input for this is a decimal to BCD in output. So you will one of the lines will be active, 5 for example. So 5 is a decimal number, so accordingly a code will be generated here for 5. Okay, what would be the code for 5? If you start from MSB 0101. Okay, so that's about it. I think it's pretty simple logic. This is the logic diagram for this circuit. It is based on the truth table, which is here. Okay, so for any number, the BCD code for it, right? The BCD code is binary coded decimal. It is the same till 9. After 9, basically 10 is different. You know that 10 is displayed differently to how it is in the actual binary. So basically that this diagram is made from this table. Okay, so for example, if fourth line is high, yeah, 4, what should be the code for 4? You know that, right? The code for 4 is what? 0100, right? A3 should be 0, A2. This is actually I'm talking about, right? So if this is 4, yeah, this line will be high only, right? Only because this is an OR gate. So this is high, it will be high. Otherwise, since all of the outputs are 0, because we said this is high only, right? All of them are 0. So all of them are 0, so obviously all of these will be 0. So you get a code for 4, right? How did they come up with this diagram? Just using this table. Okay, only for this table, that's it. Like for example, if you, yeah, so look at A0, okay, and they decided how do we make A0, which particular lines are 1 1, see 1 1 1 1 1. So 1 2 3 4 5, 5 inputs in A0. As you can see, 5 inputs, 1 2 3 4 5 inputs in A0. Which are those inputs? Though these are 1, 3, 5, 7, 9. So basically all odd numbers. Yeah. And you go here and you see 1, 3, 5, go here 7 and 9. Okay, so this is how basically you will. I think if you've had a second quiz and you know how to convert a truth table into a diagram. So if you know for A0, this is how you will make. Then again for A1, you will look for where it's 1, and then similarly you will choose a gate and then insert the inputs. Now, show how the decimal to BCD encoder converts the decimal number 3 into a BCD 0011. Okay. Okay, so how we can convert 3 into this code? I think it's pretty simple basically, isn't it? Just think about it for a minute. So we have to convert 3 into this code. I just showed you in the previous figure. 3 will be 1, all of the other inputs will be 0 basically. So you can keep writing 0, 0, 0, 0. So since this is only 1, so basically this will be obviously 1. Is 3 going anywhere else? Sorry. 3 is going here as well. So this is also 1. Since this is 1, so this will be 1 also. So basically wherever 3 input is going, only those lines are 1. So it is only going two places, in this gate and in this OR gate. These are OR gates. So if one input is high, output will be high. All other OR gates, these two OR gates, they are only receiving 0, 0, 0, 0. So that is why their outputs will be 0. Simple. Now this is your encoder. Okay. What did we do here? We wanted to convert decimal number 3 to this code. So only 3 will be high, all the other inputs will be 0. And accordingly, you will just propagate this value to the gates and look at the output. Okay. Basically, so this is actually what they have done. Okay. So same thing. All right. Now, so this is an IC74HC147. This is our encoder IC because after concept we always talk about the IC. So it has 10 active low inputs and it converts the active input into an active low BCD output. So it's the same thing we did here. This is the same thing. Decimal to BCD, 10 inputs, 4 outputs. But here they were active high, over there in the IC they are active low. Okay, they're active low. And this device offers an additional flexibility that it is a priority encoder, in the sense that if there are more inputs, because we said that at one time only one input will be high, because we said that only like if it's 4 will be high at a time, one of the lines will be high, then accordingly the output will be generated. But there could be a situation when you receive multiple inputs. If you have multiple inputs, right, for example, you have an input here, you have an input here, and you have an input here. Okay, you have an input here. So priority will be given to the highest order of the decimal digit. Okay, this decimal digits are starting from here: 1, 2, 3, 4, 5, 6, 7. 8 is the highest. So basically this will be encoded. These two will be discarded. Okay, it's written here. If more than one input is active, basically, sorry, this is active low. So basically these will be 0. This is active low. Okay, all others are 1. Okay. Okay, all others are 1. So this is active low. So basically we're saying these three are active. When these three are active, so that means they have 0 on it. They are active now. So which one will be chosen? The highest order decimal digit will be chosen because 8 is the highest order, right? It was 4, 2, and 8. So this will be chosen. So basically this will be encoded. Okay. Hmm. This is the table for that basically, and this is the application. Let me just go through the table quickly. Again, the same thing, the 8 inputs here instead and 3 outputs here. right? This is a different 8 to 3 priority encoder. This is a 10 to 4 basically decimal to BCD output. Okay, this is some other kind of an encoder, priority encoder, in which lowest priority is with the lowest order decimal number, highest priority is the highest order decimal number, and accordingly so this is the table that if D0 is 1, your output will be all zeros. If D1 is 1, output will be 001, so it will be encoded, right? If it is D2, D2 means second one, so 010 will be displayed. If D3 is high, 3 will be displayed. If D4 is high, 4 will be displayed or coded, the coded value. And as you can see, they've put don't cares here. Don't care means it doesn't matter what the value is, the highest order, the decimal value will be considered. Again, this is high enable. So that is why they're considering 0. So just keep in mind it's nothing complex, high enable, low enable. Since here it is high enable IC, so that is why they're talking about 1. The previous IC was low enable, that's why I was talking about 0 being active. Here 1 is being considered active. So at one time, if D5 is high and is the highest order decimal bit which is high, others are 0, then it doesn't matter the lower ones are high or 0. Only this will be encoded. Do you understand? I'll give you two examples just to clear it out. Okay, so the number is 0001011 1. Okay, this is the input on these lines. Okay, this is obviously the LSB, the D0. Okay, and this is the MSB, D7. Okay, now this is the number. So which one will be encoded, you think? Hmm? Which one will be encoded? So what is the highest order? This is the highest order decimal, which is non-zero. Okay, because all of these are 0, so this is the highest active line in decimal, highest order decimal line which is active. These are high, but it doesn't matter, they are lowest, they have low priority, because we said D0 has the lowest priority. The priority, this would have the highest priority, and this is how the priority is increasing, right? So so basically these will be not considered. Okay, so basically what will be encoded? uh, D0, D1, D2, D3, D4. This is D4. So D4 will be encoded into what? What is the code for 4? The code for 4 is 100. As you can see here, this is D4, this is the code. So this will be the output. It doesn't matter, these lines will not be considered. Okay, I repeat, what have we done so far? We have talked about encoders. What do encoders do? Encoders accepts an active high level, or active level, basically doesn't matter, active high or active low, depends on one of its inputs, and convert it into a coded output. Okay, receives input on one of the lines and converts it into a coded output. However, it can receive input on multiple lines as well, and that's where the priority comes. If it receives input on multiple lines, the highest order decimal value will be encoded. Okay, so now we're done. Now this is the example of encoders. In this example, a keypad is being shown, it's just an encoder, again, low enable IC is being used, 74HC147. As you can see, different keys are being shown here, uh, and they are connected from 1 to 9, and it will be these are just decimal values. This is also just decimal to BCD. They're showing you the application where decimal to BCD is actually used. So decimal to BCD is being used to for keypad interface. Okay, all right, now this is right. Now, another type of encoding is where you convert between different, type of codes. Okay, so right. So there are two examples that are 4-bit binary to gray converter. Okay, if you remember gray, gray code, in gray code, um, when two numbers basically do not change in more than one bits. Remember, we talked about this, that 0001, and yeah, so the other number in normally we represent like that. Yeah, but in gray code we will write 0001, one bit is changing, and then 1 1, and then 10. So this is our gray code, 2-bit gray code. So here to here only one bit is changing. However, here to here two bits were changing. 0 is becoming 1, 1 is becoming 0. When you go from 01 to 11, only one bit is changing. So this is gray code. This is, the feature of the gray code. So what we're doing here is we are converting 0111, this is the binary number, into gray, and then from gray to binary again. See, this is binary to gray, and this is gray to binary. So now we will have this number which is 0111. So they have, we did not have to design the encoder. It is being shown that, we can use this particular kind of, um, combination of XOR gates, which, work on the, that, in XOR gate, if the two inputs are different, the output will be high, right? So 0 and 1 are being XORed, and what you receive is uh, a 1 here. Okay, this 0 will be propagated just like that. Again, 1 is going here, 1 is receiving here, XOR gate 1 1 0, because we know that, if the inputs are same, the output is 0. Again, inputs are same here, output will be 0. Okay. Okay, so now this code, this is the 3-bit. This I showed you 2-bit gray code. Now this is a 3-bit gray code. Now 3-bit gray code is being converted into 3-bit binary is being converted into 3-bit gray code. Okay, so it's a very simple encoder that is being designed to show to convert from binary to gray. Just remember this thing, okay? And this is the circuit diagram for gray to binary. If you want to go from gray code to binary code, as you can see, it's like a feedback kind of a thing. You start here, this output is becomes its input, its output become this input. Okay, so I'm not going into the logic of why we developed it like this, why is it like that. We're just, using this particular encoder to show you the concept of encoding. Okay, that how we can go from one kind of number system to the other, or one kind of code to the other. So we can convert a gray code to binary code like that. Now again, this was our number 0010, so we can convert it from gray to binary. Now all the inputs are there, just propagate them. 0 is here, 1 is here. 01 means what will be the output? 1, right? Because we know that our XOR gate gives you high output when your inputs are different. Now this 1 will come here. So 10 again, it will be 1, right? Now this 1 will go here. 10 again, 1. So, and this 0 is as it is propagated, MSP. So what is the output? 0111. Or basically this was our number. So what we've done is we went from binary to gray, and then gray to binary. Okay, this is just an example to get you guys. I think it's the, oh, it's just another example. Okay, nothing complex, just another example being applied to the same logic. Okay, 1010, just propagate it, and you will get this output. 0 as it is, 0 goes here, 1 here, 0 1 1. Okay, 1 here, 1 0 1, 0 here, 1 1 0 1. Okay, so again you will apply the same uh, on this circuit, just okay, no, this is not reverse, this is another number. Another number is gray code 101. Okay, so 1011, this is the gray code, this is circuit for the gray code conversion to binary. Just propagate the values. Okay, so the next concept after, decoders and encoders is our multiplexers and demultiplexers. Now, in multiplexer, what is a multiplexer? Multiplexer is basically it's a device which selects from multiple lines of inputs. Okay, it allows information from several sources uh, to be routed on a single line or a single output line for transmission. So you are receiving input from multiple sources, and the device will route it, one of the inputs, to the outputs. Okay, if I can give you a very simple example, it's out there's a room, and at the door, outside the door, multiple, people are standing, but only one person can come at a time. So basically, you can call these the people. Okay, this is the door. So through this door, only one of them can pass to the output. Okay, so these four people are standing, D0, D1, D2, D3. Only one of them can pass through this door to the output at one time. Okay, now how do we decide which one should go first or which one should go after? These select lines will determine that. All right. So if these select lines will call out a particular name like D1. Okay, so the code of D1 will be displayed here. The code of D1 is, one line. So basically this is the code 01. So 01 will be, or just like, you're calling out the name, you're saying, Mr. This, you can pass through the door. you know so just like that, so that code is being displayed here, 10. Okay, uh so yeah, so 1 and 0, that will be the code. This is MSB. So 10, so when 10 is displayed here, that means D1 code has the priority, or D1 code is being allowed to go through this door to the output. Okay, so this is a multiplexer. It selects one line. Okay, it selects one data line from two or more input lines and route the data from the selected lines to the output. Whichever the selected line is based on the the select lines data, that will be routed. Data is here. These are the select lines which are going to select which data line will be routed. Okay, the particular data line that is selected is determined by the select inputs. Okay, so the select inputs are selecting which data line can be connected to the output. Okay, so that's very simple concept. If I just give you an example, for example, there is data here, and there is, like, all the lines have some data. Okay, all the lines have some data, and the code is 1 1 here. Which line should be routed? Now 1 1 is the code basically for which one? D3. Now you don't have to memorize this table. D3, 3 means the code should be 1 1. 2 means the code should be 1 0. Yeah. So D3, 1 1 is the code, so it's for D3. So basically this line will be routed and connected to the output. Okay. Very simple. All right. Oh, okay. So they have also there is also an example. Now another example is saying that the select line is 0 1. Now, if it is 0 1, which line should be selected? 0 1. MSB is 1, so that means 2, or you can see here as well. 0 1. See, S0 is 0 and S1 is 1. So 0 1. What is that? D2. So that means D2 should be selected. Okay, yeah. All right. Okay. Now there's a timing diagram here, and yeah, so it's very interesting, way to explain to you the concept. Now let's have a look. Okay, now here, uh, D1, D0, D1, D3, D4. These are our uh, data lines, and these are my select lines. Okay, so the data has been provided on the select lines, and the data has been provided on the data lines. Okay, so now we have to decide what will be the output. Now that this is my output here. Okay, what should be the output? Now let's quickly look at it. Now the data is what? The data is, obviously, this is 0, this is 0, this is 1, right? This is 1, this is 0, and this is 0. Okay, but it doesn't matter what the data is. And sorry, this is also 0 here. Yeah, so this is the data, but which data should be put on the output line? The select data is saying 0 0. 0 0 is the code for what? D0, right? D0. 0 1 is the code for what? D1. 1 0 is the code for D2. 1 1 is the code for what? D3. Okay, so now this is the code. So what will be displayed here? D0 will be displayed here. D0. What is the data on D0? You go to D0, 0. So 0 data. Okay, now second one. What is the select line is saying? 1 0. S0 is 1, S1 is 1, 1 0, meaning 0 1. 0 1 is D1. So whatever is the data on D1, that will be copied here. D1 has data what? 1. So 1 will be copied here. So it will be high for this particular cycle. Again now, let's look at now this one. What are the select lines? 1 0. 1 0 is what? D2. So D2 line, where is D2 line? The data on D2 line is 0. So D2. So you can also write here, that which particular data you are writing here. D2, this was D1. Okay. Now here, what are the select lines? 1 1. 1 1 is what? D3. So D3 data will be output and D3 is 0. So it will remain the same 0 for this particular cycle. Do you understand? So this is how you will do it. Okay, so you first look at the data lines, the select lines. What is the what are what which line should be routed to the output? The select lines are telling you, right? This is what we did previously, right? So all the lines had data. Which one should be put on the output line? It depends on the select lines. Which name is select line indicating? Which input line is select line indicating? So the select line is telling you 0 0 code, meaning D0 data should be routed to the output. Data on D0 is 0, that data should be copied on the output. Second clock cycle, 0 1. 0 1 means D1 should be selected. Okay, D1 is, what's the data on D1? 1. So 1 will be copied here. Okay, hopefully this is clear, and as you can see, this is the same data line that they have shown. All right, moving forward now, demux. So demux is the opposite of mux. Okay, in multiplexer you had multiple lines and you had to choose which line will be selected based on the select lines to be routed to the output. Okay, now in demultiplexer it is the opposite of the mux. So basically there is only one line at the input. Okay, this will be the basically the input line. Yeah, there's one line. It switches data from one input line to multiple output lines. Okay, so it's like you have multiple doors and only one person at the input. So that we now the select lines will tell you that one person will go through which door. Okay, who will tell how will we select the door based on these select lines. So there is data, multiple data stream are coming, waveform is coming. You will decide at one time, 0 0 0. So it will go to y0. Then it will say 1 0 0. So it will go to 1. Okay, so just like that. So this is my IC 74LS138. This is also used as a decoder IC, 328 decoder IC, but this can also be used as a demux. Okay, data is applied to one of the enable lines G1. So basically here data is applied and routed to the selected output line depending upon the select variables. Whatever the select variables are saying, according to that output will be this input will be routed to the selected output line. Okay. Okay, so this is a table that I inserted separately. So this is our input. So if the input is 1, yeah, there is some input. Yeah, there is some value. Now, what are the select line data? Select line data is saying 0 0. Okay, meaning 0 0 line should be selected, which is y0. Okay, so y0 will be selected and the data will be placed on that particular line. All other lines will be 0. Okay, then select lines are 0 1. 0 1 means what? Y1 obviously. So Y1 data will be placed on Y1, all other lines are 0. Okay, so on and so forth. So this is our demultiplexer. Let's have a look at this example. Okay. Uh, okay. Now, oh no, I did not want to show you the output yet. Let's try and make it ourselves. Determine the outputs given the input shown. Okay, this is our demultiplexer. My input line is G1. Okay, this red color line, this is my input line. These are my select lines. And these are just enable inputs, low enable, so that is why they are continuously low. Now how should the output look like? Okay, okay. And this is obviously low enable. So just keep in mind, we have to think about that. The input is high enable and the output is low enable. So whatever will be the input, we have to place the opposite of that on the output lines. As you can see here, see, this is high enable input, but output is low enable. So meaning if input is 1, output will be 0. If input is 0, output will be 1. Okay. Now initially the output is the select lines is what? Select lines are telling us 0, 0, 0. The data is what? Data is 1. Okay, so the output should be 0, but on which line? 0, 0, 0 is the code. The code corresponds to y0. Okay, the code for y0 is 000. For y1 is 001. For y2 is 010. Right? I think you know these codes, right? For y3 is 100. Right? Now, so what will be the data? Data will be 0, but on which line? Y0, because the code is 000. So here, okay, the first data is here and it will be low. Okay, it will be low till this particular cycle. Okay, obviously I don't know after that what will happen, but we have to now go and check the next clock cycle. This is the next clock cycle. Okay, this is the first clock cycle. This is the next clock cycle, second clock cycle. Now in the second clock cycle, what is my select line saying? Select line is saying 1, 0 and 0. So basically 0, 0, 1. Where is 0, 0, 1? Y1. So that means my output will be displayed on Y1. Okay, what will be displayed on Y1? Well, in this line, this is my data. Data is high, so again, it will be low. So from this line to this, it is high. Okay, and remember that this was low, so now this will become high. Okay, for this line, this will be high. And obviously, before that, this was high. Okay, all the other lines will be high. Okay, only y0 will be low. Here only y1 will be low. Okay, all right. Now we're gonna be talking about this clock cycle 3. Because see the output, if I just show you here, the output is on one line only. All the other lines are 0 here. Okay, all the other lines are 0 here because obviously this is high enable. But when we talk about here, if the input is 1, the output, that particular select line will be 0, all other outputs will be 1. Okay, all right. Do you want me to explain further? See, if the select lines are 000 and the input is 1. Now this is low enable. So based on the select lines, Y0 will be selected, meaning output will be generated on this line. Okay, so input will be connected with Y0. But what will be the data produced? It will be the opposite of this because this is low enable. So 0 will be produced here. All the other lines will be 1. Do you understand? Select lines are, what is the procedure? Look at the select lines. Which data should be routed on which output lines? Okay? Okay? So the input is high, select lines at 000, y0 will be selected, that line will become 0. That line will become 0 and all other will become high. Okay, all right. Okie dokie. All right. Now we will look at this third cycle. In third cycle, the select lines are 0, 1, 0, which means y2 output will be generated on y2. Okay, output will be generated on y2, and again for these two lines they are high. Now this is my third clock cycle. So in this clock cycle, my output is high. So output is high, which means my input is going to be low. So this will become low. Okay, all right. And these two will continue to be higher. And this one will become high. Because all other will be high, only this particular will be low. Okay, now what I'm gonna do is I'm gonna erase use the eraser to erase all of this so that I can show you the actual waveform and you can clearly see. There you go. Okay, so these are the same that I drew. Now for the fourth cycle, what are the select lines? 1 1 0 1 1 0, yeah, 1 1 0 0 1 1. Oh yeah, okay, sorry, I think I made a mistake here. It's 0 0 1 1. 3 is 0 1 1. Okay, all right, so 0 1 1. Now so 0 1 1 means y3 will be selected. What is the data? The data is 0, so meaning the opposite, meaning 1 will be generated here. As you can see, it will continue to be 1. So yeah, this is how it is. If you don't understand this, I will explain this further in the class. Okay, now the last topic is parity generators and parity checkers. So we talked about parity in, I think, second and or third chapter, the even parity and odd parity, and you know that we use it for data, checking, error correction, well, error detection basically, not correction. We try to detect the error during transmission of data using this parity bit. In even parity, the total number of ones should be even, including the parity, and in odd parity bit, the total number of ones should be odd, including the parity bit. So if you have this number, ASCII letter S, then show the parity bit for the letter S with odd and even parity. So it's very simple, this is my number and I want to add odd parity with it and even parity with it. So if you look at it, how many ones are there? 1, 2, 3, 4, right? So in case we want to add odd parity, so that means in odd parity, the parity, including the parity, the total number of ones should be odd. So here, as you can see, there are 4 ones. So there are 4 ones, so that means parity bit should be 1, right? So that will make the number of ones to be odd. Okay. All right. Now, again, this is my data, and I have to add even parity with it, right? So for even parity, the total number of ones in the data, including the parity, should be even. So it's already even, isn't it? 1, 2, 3, 4. So it's already even, so I should make this 0. Simple as that. Okay, right? So this is even and odd parity. Okay, so we have an IC which is 74LS. EEN210 IC, which is used to generate a parity bit, okay, or to check an incoming data stream for even or odd parity. So it is dual purpose, meaning it can generate a parity as well as it can check the parity as well. Okay, it can generate a parity and it can check the parity as well. Okay, how can it do both the things? Let me that this IC is dual purpose. So it checks for parity as well as generates parity as well. So, either ways you can check it. So if, for example, you have, um, let me just try to, yes. So if you have already have, parity is attached with the data and you want to check, whether the data has, odd parity or even parity, that's fine. So it will be checking it, right? Yeah, so accordingly it will generate the output. So the checker, what does the checker do? It will determine which parity does your data have. So if the data has odd parity will be high, output will be high. If the data input has high even parity, then the even parity output will be high. Simple. Otherwise they will be low. So uh, let me just write the data here. Okay. Sorry. Hopefully you can see the screen now. Yeah. So this is my data bit, and I want to determine whether its parity is even or odd, right? So what will I do? I will just check for the number of ones, right? So the number of ones are even. Okay, so the number of ones are even, so I am saying that it has even parity. So even parity will be high, and odd parity will be 0. Okay, according to these inputs and outputs. Okay, so even parity line will be high and odd parity will be 0, right? Very simple, right? So you have this data and we are checking whether it has even parity or odd parity. Now, how will we generate the even or odd parity? So what the generator actually does is, as you can see here, that if you want to generate even parity, the parity bit is taken from the odd parity output. Okay, so now you have this this IC, use this IC with the data, and how you can generate the parity. So you have the data, add with it the odd output pin if you want to generate even parity. Okay, now you won't understand it unless I don't explain it with the example. Okay, now going back to our example. Now I want to generate even parity for this. Okay, so I want to generate even parity for this data. For some data, right? So it doesn't have a parity. I have some data. I want to generate parity with it. So for even parity, use the data and append with it the parity bit of which one, which output? The odd one. If you want to create even, odd output. Take the odd output, which is what? 0. So it works fine, right? Overall, my parity is even. However, if you want to generate odd parity, take the data and append with it which output? Even output. What is even output? 1. So it will generate odd parity for me. And as you can see now that it has odd parity, right? It's very simple. Okay. So hopefully you understand this. So what is it saying? To generate parity, the parity bit is taken from odd parity output, and to generate odd parity, output is taken from the even parity output. So basically this IC you will use, you have some data, you want to generate the parity, just feed the data into it, look at these outputs and just append them accordingly. Okay, that's it. But however, if you have a data which already has a parity bit and you want to check what parity it is, give the data, to the inputs and look at these outputs. So it can do both the things for you. That's about it. This is the end of our chapter. We'll discuss, further examples in the class.